At a sunny harbor, Qubit watched a huge submarine resting on the water like a steel whale. Then it slowly slipped beneath the waves. Qubit's antenna tilted in disbelief. That machine weighs thousands of tons. Why does it not sink like a dropped tiffin box, and how does it choose when to dive? The first law is buoyancy. When an object enters water, it pushes some water out of the way or displaces it. The water pushes upward in return. This buoyant force equals the weight of the displaced water. If that push balances the object's weight, the object can float. Shape controls how much water is displaced. A solid block of steel is dense and usually sinks. A submarine is a large hollow shape containing air, machinery, supplies, and people. Its mass spread across its full volume can make its average density lower than seawater, so it displaces enough water to float. To change that balance, submarines use main ballast tanks built around the strong inner hull. At the surface, these tanks contain plenty of air, making the submarine's overall average density low enough to float. Openings at the bottom connect the ballast tanks to the sea, while controllable vents near the top manage whether air stays trapped or escapes. When trained crew members order a dive, they open the vents. Air leaves from the top and seawater flows naturally into the ballast tanks through the lower openings. The submarine becomes heavier without becoming much larger, so its average density rises. When its weight exceeds the buoyant force, it gains negative buoyancy and begins to descend, smoothly, carefully, and under constant monitoring. The crew does not usually fill the main ballast tanks with a giant pump. Sea pressure helps water enter as air is vented. Engineers watch depth, angle, speed, and tank condition on redundant instruments. Real submarines require qualified teams. Diving one is never a do-it-yourself activity or swimming pool experiment. A submarine does not want to keep falling. It aims for nearly neutral buoyancy, where weight and buoyant force are almost equal. Smaller variable ballast and trim tanks take in or release measured amounts of water. Moving water between trim tanks balances the bow and stern, like shifting a school bag until it sits comfortably. Buoyancy provides the broad up or down tendency, while control surfaces fine-tune the journey. As the submarine moves, water flowing over hydroplanes creates forces that angle the vessel downward or upward. They work somewhat like an aeroplane's wings, but in water. Without forward motion, they have far less effect. Motors turn a propeller or pump jet to drive the submarine ahead. A rudder steers left and right. Hydroplanes control its vertical path and pitch. The crew combines propulsion, buoyancy, and control surfaces instead of relying on one magic dive button. Qubit tried an imaginary button anyway. It produced one serious-looking bubble. As the vessel descends, water pressure increases by roughly 1 atmosphere for every 10 meters of seawater. Pressure acts from every direction, not only from above. At great depth, the outside water can squeeze with enormous force. This is why a submarine has a carefully engineered pressure hull, tested to remain strong within a strict safe operating depth. Many submarines have a rounded cylindrical pressure hull because curved surfaces distribute force efficiently. A streamlined outer hull shapes water flow, while spaces between hulls can contain floodable tanks and equipment. The inside stays dry and near comfortable air pressure. The sea does not press directly on the crew. Most submarines do not need windows, and large flat ones would create weak points. Some research submersibles use extremely thick, specially shaped viewports or transparent pressure spheres designed by experts. Cameras and lights reveal the deep too. Ordinary glass, sealed boxes, and improvised containers are dangerously unsuitable underwater. Life support is as important as the hull. Systems provide oxygen, remove carbon dioxide, control humidity and temperature, and monitor the air. Fresh water, food, power, fire protection, and backup equipment support the crew. For its voyage, a submarine is a carefully managed underwater habitat. Because light fades quickly underwater, submarines often listen. Passive sonar detects sounds already in the sea, while active sonar sends a pulse and measures returning echoes. Travel time helps estimate distance, but sonar is not magical eyesight, and echoes require expert interpretation. Research missions use it responsibly around marine life. To return to the surface, the submarine must regain positive buoyancy. High-pressure air is released into the main ballast tanks, pushing seawater out through the lower openings. With less water aboard, the vessel's average density falls, and buoyancy lifts it. During a normal ascent, the crew also uses forward motion and hydroplanes for a stable, controlled climb. Submarines carry backup procedures for emergencies, including powerful systems that can blow water from ballast tanks rapidly. Some small research craft may also carry releasable ballast weights. These are engineered safety features with strict checks, not dramatic toys. Crews train repeatedly because underwater problems must be handled calmly, correctly, and with reliable equipment. Nature solves similar balance problems in different ways. Many bony fish adjust gas in a swim bladder to change buoyancy, while sharks rely more on oily tissues and constant swimming. A submarine is not copying either animal exactly, but the comparison reveals the same useful question: how can weight, volume, lift, and motion be balanced in water? So here is Qubit's deep sea recap. Displacement creates an upward buoyant force, ballast water changes the submarine's average density, trim tanks balance it, hydroplanes guide it while moving, and a strong pressure hull protects the habitat inside. Air pushes ballast water out for surfacing. The submarine rose beside the harbor, and Qubit saluted. Excellent. A steel whale with very good maths.